Okay, hi and welcome to Notes 1.7. In this set of notes, we're really going to talk about the base of all algebra here. This is the stuff that kind of makes your understanding of algebra, your operations later. What you'll do usually in this class is you'll get really good at it in the first semester. And then as time goes, you'll tend to, and you'll learn new things, you'll tend to start mixing them together. So if there's ever a section of notes that you really need to know, it's in this first unit here. Even the notes that come after this, 1.8 super important, and the stuff we did in 1.1 and 1.2, those terms are huge. So if you ever get confused in what to do and what goes together, this is the place all year that you want to come back to. This is the stuff that seems super easy, but when we get more complex stuff, you start to forget the base rules. So now that we've got that out of the way, let's go ahead and talk about some of the things we're going to do today. We're going to go ahead and look at like terms, and there's a little LT to stand for that, and we're going to explore the distributive property in this particular notes. And in the next notes, 1.8, you'll talk about real number properties, which is also as important. So from pulling from the other day, we learned what an algebraic expression was. We generally say expression versus algebraic expression, but you get the idea. This is an algebraic expression right here. Okay. In that algebraic expression, we saw some simpler ones the other day, but this one's got, well, if you look at it, 1, 2, 3, 4 parts to it. And there are variables in it. There are constants or numbers in it, and there's even some exponents in here. What we want to do is look at each expression in terms of its parts, and those parts we're going to give a specific name to, and this we will use all year long. It's what we call a term. It can be a number by itself, like 12. It can be a variable, even by itself. If we wanted to add another one over here, we could. That could be a term. It could be a product or a division of a combination of those. So you can have a number times a variable, even raised to an exponent. This whole thing right here is one term of this expression. Here's another term. Negative 5ab, that's another term of this expression. 3b is a different term of this expression. And then negative 12 and x, if we wanted to keep it in there, those would both be terms. Okay, so the number of terms is important, and looking at these in understanding what a term is. A term, again, is a variable or number combination that are a multiplication or division together. They're separated, and this is key, separated by some operation. Well, and when I say some operation, a very specific operation, addition or subtraction. So products being multiplied together makes them a term, and then we separate terms in an expression by addition or subtraction. All right, so now that we kind of got that idea of a term, you've probably seen it before, maybe you remember learning terms before, but now we've got a very clear understanding of what a term is. Let's talk about a couple other parts that we see here. A constant then, right, a constant is a number in an expression or a term that doesn't have a variable. It's just a number, right? So there's your constant. Negative 12 is the constant of this expression. Any numbers by themselves are referred to as constants if they don't have a variable. They can be different numbers, but we call them constants because they don't have a variable. They're not going to change. That kind of makes sense. They're consistently, in this case, negative 12. All right, so let's look at another one here. We've got the coefficient. A coefficient is another number, but this number we can find in front of a variable. So these numbers in front of a variable, and that's generally where we put our numbers when we're talking about terms and expressions. We put them in the front. You don't want them in the back. There's reasons for that, but we'll keep that simple for now. Put them in the front, put the variable next. Okay? These are what we refer to as coefficients. So if we're talking about a constant, we're looking for a number with no variable. If we're talking about a coefficient, we're looking for the number in front of the variable. Okay? Now, let's move down to what we're going to kind of focus on here for a second, which is like terms. Now we've got a bunch of terms here. Here's one term, two terms, three terms, four terms, and there's that other one that we added in, which is an x. That's a fifth term. There's 5 terms to this expression. Now, not all of these terms are the same. Actually, none of these terms are the same. So the reason that they're not all combined together is because they're not like terms. What we want to talk about is like terms. Those terms we need to put together if they're alike. Well, what is a like term? They have exactly no variance, exactly the same variable. Okay, that's what makes them a like term. they have to have the exact same variable, not just an a. They have to have an a, or if it's an a and an a squared, they have to be exactly a squared. What does that mean? Let's look at some examples here. That'll probably clear this up a little bit. Here are some examples of like terms. We've got a 3x and a negative 2x. I agree, the 3 and the negative 2 are not the same, but that's not what we're looking at. We're looking at the variable. And the variable in both of these terms here is x. And since they're the same, we would put those together. We would combine like terms. It's like a rule, or it's kind of like an indicator of something to do. If you see like terms, put them together. What does that mean to put them together? Well, remember that terms are separated by addition and subtraction. It means you're going to add or subtract them depending on what their sign is. Okay, looking at the next one over here. Negative 5x squared and 9x squared. Again, doesn't matter about the negative 5 and the 9. All we care about is that it's x squared exactly. Okay, and again, repeat this case, xy and xy. This is a negative 1. I think we all knew that, right? That's the coefficient of that second one, but we would combine x and y. Yeah, you're like, Mr. Hallam, wait, there's two variables. Yeah, they're the same variable combination. So it's got to be exactly x and exactly y. If we had a square here on the y, we wouldn't be able to combine those. Those would be not like terms. So they have to be exactly the same with the exact same exponents. Okay, and then you can see one on the bottom here, kind of an example of that. X squared between both terms, and y cubed between both terms. We would combine these terms. You're like, well, there's a lot going on. I'll show you how to combine them. You don't have to worry that those variables have a exponent to them when we combine like terms. You don't have to worry about that. You can actually ignore it in this case. All right, so a couple quick examples of not like terms. X and y, not the same. Y and y squared, not the same. Y and xy, not the same. X squared y and xy squared. Notice the placement of the square matters here. This indicates this x is squared. This indicates over here that the y is squared. So they're not the same exponents. All right, so now we're pretty clear on what like terms are and not like terms are. Let's talk about combining them, because I've been throwing that around a little bit. So combining like terms, again, terms are separated by an addition or subtraction, so we're going to combine them with those operations. The variables stay the same. Let's highlight that. The variables stay the same, okay, but the coefficients change. So let's add that into our note. I want to say COEFF, to stands for coefficients, right? It's change. We don't do anything with the variable. That's the part I need you to know. Just the coefficient. So let's look. So we've got a 3x squared plus a 5x squared. We recognize those as like terms, x squared and x squared. So these two terms, 3x squared and 5x squared, are like terms. We're going to combine those like terms. Here's what happens. We never write this, but I like to show it at the beginning of the notes or stuff that we don't normally do. Remember, math is efficient. So things that we could write, we might not write if it's common and it takes extra time. So in this case, we would never really write this, but I want you to see what actually happens. What we're going to do here is it kind of separates out, and we just end up combining just the coefficients here. So we know that they're going to go together. We know that our variable is going to stay the same, but our coefficients are going to take whatever operations they are. This is a positive 3, and that's a positive 5. Why do I know that's a positive 3? Because there's no negative in front of it. Why do I know that's a positive 5? Because there's a positive in front of it. So I'm going to add those two, and what we get is 8x squared. Notice the variable stayed the same, and the coefficient changed. That's what you have to know for like terms. This rule, don't forget, okay? This is one of the most important rules all year. So let's look at another one. We've got three terms in our expression. We've got a 4x, a 7x squared, and a negative x. So let's identify the ones that are like terms, this x and this 4x, or I should say negative 1x, right? Because we omit the 1. That's part of that efficiency thing. So we take those two like terms, we want to put them together. So remember what happens. We're going to take the coefficients, negative 1 and 4, we're going to combine them. Well, what is 4 minus 1? It's 3. The variable stays the same. And then this part, nothing happened to it. So we just drop it down. We can't combine it in, right? Because it's not a like term. It's an x squared. So we can't combine it in. So it just comes through. It's a positive 7x squared. So we'd write it like this. Now, really, if we're going to get a little bit further along, we like our largest exponents in front. So you may see, if this was a question in the book, you may see them rearrange the larger exponent. So meaning this squared is larger than this x with a single degree there. I know you can't see the ones, right? It's part of math. That would go in front. If you don't get that right now, that's perfectly fine. But if you got here, great. That's what I would need. All right, so here's a couple other quick examples. Negative 5c plus 5c, like terms. The c's are exactly the same. This has an imaginary 1 in front of it. So 1 and negative 5 makes negative 4. The variable stays the same. You're like, whoa, Mr. Hallam, look it over here. We've got a couple like terms and a non-like term. That's perfectly fine. The like terms you can see are identified here in parentheses. That's an x squared with a negative 2 and a positive 2. So we're going to combine the coefficients. Negative 2 and positive 2 turns to 0. Right? And you're like, what happens to the variable? Well, if you want to write it in there, let me get a different color here. 0 times x squared, right? Because they're multiplied. We said that they're products. We said that right above, right? What's 0 times x squared? 0. So the variables go away because it's being multiplied by 0. So the only thing that's there is this not like term, and that's what our result would be. All right, so let's add one more thing in there before this video gets too long. Let's talk about the distributive property. Again, a key piece to everything you're going to do this year. The distributive property simply is, if you have a set of parentheses, whatever's in front of it, you're going to multiply to everything inside. So what do I mean by everything? All the terms. Each term will get multiplied by whatever's in front of the parentheses. Each piece of the term. So what does that look like generically? This is the math side of stuff here. If I have some value out front, some term, and I've got some parentheses that it's multiplied to, right? Notice there's no operation between the a and the parentheses. I'm going to multiply it to whatever b is, that term, and I'm going to multiply it to whatever c is, that term. And the operation between them stays, right? Because they're added, and I'm just multiplying this piece out front to both of the terms inside. So it becomes a times b plus a times c. Or if there's a subtraction sign, the subtraction sign comes down. So what does that look like? Well, let's do one. We're going to jump around here. We'll come back to question 1 here. Let's do number 3 because that directly applies to the distributive property. And then I'll show you what it's good for. All right, so this 2 is a term. It's called a constant. And then inside the parentheses, we have the quantity of 5x plus 3. So a term, 5x plus 3. They're not like terms, so they're not combined, right? So I've got to take this 2 and I need to multiply it by both terms inside the parentheses. If there was 3 terms, I'd multiply it to 3 terms. If there was 4 terms, I'd multiply it to 4 terms. But we're going to multiply it to each of those terms. So 2 times 5x, and again, with this multiplication here, the coefficient's going to change. So it's 2 times 5, which is 10. The variable stays the same in that case because it's a multiplication, different from addition. Right? And then we got 2 times 3. There's the operation plus that came down. 2 times 3 is 6. That's what the distributive property looks like. You can see in 4 here, it's already pre-done. We've got 3b minus 2, and it's multiplied by the constant 1/3. So we take 1/3, multiply it by 3b. Well, 1/3 times 3 turns into 1. The b comes along. B times 1 is just b. 1/3 times 2, right? The negative drops. Sorry, I forgot that. The negative just drops down because it's coming along for the ride. And 2 times 1/3 is 2/3. And again, here's one with a negative in it. A negative counts as a constant. It's a negative 1, right? If there's no operation between, it's a negative 1. So really all we're going to do is take negative 1 and multiply it by both of these terms. Well, if this is a positive 6x and we multiply it by a negative, guess what happens? It becomes a negative 6x. That's what multiplying by a negative 1 does. It changes whatever sign is there. Well, this is a positive 4, so it's going to multiply to a negative 4. Here's where the distributive property can apply to something you're doing today. So if we're going to use the distributive property on this example here to make that easier, can you multiply 34 times 102 in your head without a calculator? I'm not so good at it, but let me show you a trick. So when you see people do calculations quickly on those shows and you see really smart people doing fast calculations, this is one of the tricks they use. We're going to use the distributive property. Okay, hang with me here. I'm going to take 34 because I know I have to multiply it by 102, but I want to change 102. I want to make it look easier for me to do the multiplication in my head. So I'm going to keep 102 the same, but I'm going to make it look different. 102 is the same as 100 plus 2, correct? 100 plus 2 is 102. Nothing different. We haven't changed anything. We just made it look different. Now we're going to use the distributive property to multiply. Can you multiply 34 times 100? I'm pretty sure all of you could. Then we're going to use the distributive property to multiply by the other term that's in the parentheses, which is 2. Can you multiply 34 times 2? I'm sure you can, right? So 68. Can you add 3,468? Now, you just multiplied 34 by 102 without a calculator in your head. Here's another quick example before I'm done. I know this is a longer video, but hang on. So this one's going to ask us to find the total cost of 8 sandwiches. It costs $2.99. Now we could say 8 times 3. That's pretty close to what we do. We'd estimate that. But if you take that a step farther, you can actually get the exact answer by taking, instead of 8 times 3, 8 times 3 minus 1. Well, why would we want to multiply 8 times 3 minus 1? Because what we did is took $2.99, made it 3, and then subtracted a penny off. Here we broke $2.99 up into an easier an easier way to look at it. So we're going to take 8 times 3. There's your $24. And then you're going to take 8 times 0.01 or 1 cent. You're going to come up with 8 cents. The negative comes around. 24 minus 8 cents is $23.92. So you can find an exact answer doing that instead of estimating. It's a very handy trick. You can do these in your brain, and that's what all these people on TV do when they're doing these quick calculations. All right, you have your homework. I'll see you in class. There's a second part to this you'll watch right after this. All right, bye.